Hi, welcome back to our second video for 6.1 sequences as discrete functions. In this video, we're going to perform the investigation. So this is actually the investigation from page 354. You don't need to go to your textbooks though, because we have everything in this handout that we need. Feel free to pause the video and complete this on your own, and then come back and watch the video to check your answers. So it says, how can you relate each number in a sequence to its position in the list? So if you look at this table, we have the number of squares here, which have to do with this geometric pattern, the number of squares. And then on the right side, we have the number of regions, which would have to do with the enclosed regions inside the pattern. Okay. So it says here the pattern of floor tiles at a new hotel is designed using nested squares. That's when we place squares inside of squares. Explore the sequence formed by the number of enclosed regions created. So when we only have one square, there's only one enclosed region. So that would have been at the beginning with just this one square. Then when we add a second square inside, so two squares now, the number of enclosed regions is going to be 5. 1, 2, 3, 4, 5. Okay, what about when we have 3? So let's switch colors just so that we can see here. So we still have our previous amount, the 1, 2, 3, 4, 5, but now we've added some more here. So we would have 4 plus 5, we'd have a total of 9. Okay, you can go ahead and count those. Now when we do 4 squares, we'll have the previous amount, but because we're drawing the square in here, you can see we're creating 4 new enclosed regions. So we would have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's basically the previous amount, but when we draw this third square here, we're creating 4 new spots. So we go from 9 to 13 by adding 4. Okay, and then we'll erase that here. We have to have 5 squares now, so we're going to add a fifth one in. Still the same amount of squares, except we've added 4 new spaces. So we would have 13, 14, 15, 16, 17. 17 spots. So what is the pattern in the number of regions column? So what's the pattern in here? Well, we can see we're just going up by 4. Well, by 4 each time. So we'll say increases by 4 for each additional square added. Okay, so every time we add a square, we create 4 new enclosed regions. Write the values in this column as a sequence of terms. So write these as a sequence of terms. Use the pattern to write the next 3 terms in the sequence. So we start with 1, then we have 5, 9, 14, or 13, sorry, 13, 17. And now to write the next 3, I would just have to keep going up by 4 each time. So plus 4, and I would get 21, add another 4, get 25, and add another 4, get 29. So those are the next 3. Graph the sequence using ordered pairs of the form n, comma, t. So n is the number of squares, t is the total number of regions. So this would be n versus t. So when there's one square, we only have one enclosed region, right? So I just plotted this point. Then we'll do 2, 5, 3, 9. Oh, it looks like my 1 was in the wrong spot here. 1, 1 would be here. 2, 2, 5. I would have to go up to 5. That'll be right there. 3, 9. 3, 9 would be up here. And then 4, 13. That would be here. And that's probably all we're going to get for that. Okay, it says, should we join the pots and join the points and draw a smooth curve or line through them, or should we leave them as distinct points? Explain why or why not. So I've graphed these points, and think about what the points represent. The number of squares drawn, 1, 2, 3, 4, 5. These are the number of regions created. If I draw a line through them, then what I'm doing is I'm including all the infinite amount of points along here. And I know we're really used to doing this in math class, but when we look at the context, like the number of squares, these have to be whole numbers. We can't draw half a square or, a 0.1 of a square. So it doesn't make sense to draw a line through here. So we should leave them as discrete points. Okay, that's just because like the points in between don't exist. Then it says determine an explicit formula to describe the number of regions, T of n, according to the number of squares. So notice we wrote T a little bit different. We wrote it as T of n. So this is like telling us the term number. So this subscript n, we could write like T1 for first term, and then T2, that would be the second term, and so forth. So we'll write that down right up here real quick. So T of n, we could write it, this just means the nth term. Sorry, we'll say in a sequence. So what we mean by that is T subscript 1. So this T of n, it doesn't mean T times n. Okay, it's T subscript n. So it's letting us know the term number or the position. So T of 1 would mean first term in the sequence. So if I want to know the fourth term, I'd write T of 4, fourth term. Now you can see when we write T of n, it means the nth term. So that can represent any term that we want. So now we can write it as an equation. So if I would like to try to write an equation for this, so I want to relate the total number of regions with respect to the number of squares or the term number. So well, maybe I'll give you guys a few minutes to try to come up with that equation, because that is kind of an important part of this. So maybe pause the video, see if you can come up with the equation here. So we want to relate these numbers with these numbers. We know it shouldn't be too hard because these points, it looks like they form like a linear equation, right? So go ahead and try that. Okay, so to come up with this equation, I want to satisfy these points, okay? And I can tell that they go up by 4 each term. Exactly 4. So that means this is a linear equation and it actually has a slope of 4. So it's going to kind of look something like this, y equals 4x. Okay, notice that though this doesn't work for this here. So if you were trying this on your own, you probably would have realized, yeah, if I plug 1 in, if I plug 1 in for x, I get 4 out, and that's not the same number here. So it's actually 3 less, right? And same thing with this. If I plug 2 in, I would get 8, and my answer is 5, again, I need something 3 less. So if you kind of follow that reasoning, the correct equation would look more like this. 4x minus 3, where this is the slope. And you could also think of it as like this is the y-intercept. So notice our point started at 1, 1. Well, if we were to continue this back, we would have to go down 4. So we would go down 1, 2, 3, 4, and we would be right here. That would put us at negative 3. So let's write out our equation. We can say 4n minus 3. Okay, it's always good to check. Okay, so let's check with the point that we have, like 2, 5. So I could plug 5 in for t of n. Actually, let's write it like this. We'll say t5 equals 4, sorry, not t5, t2, because n is 2. Remember, this is n and this is t. So t2 is going to equal 4 times 2 minus 3, which gives us 12 minus 3, which is, sorry, 8 minus 3. Yikes, 8 minus 3, which is 5. And we can see that works. That satisfies our point. So when n is 2, the whole thing is equal to 5. Okay, that's it for our first video. Hopefully that investigation went well for you, and I'll see you in the next video.